Good morning, everybody.
Yeah.
Thanks for waking up and coming to the lecture. My name is Marios Poligarpou. I'm the chair in this morning plenary session. And it's my great pleasure to introduce today's speaker, who is also the recipient of the European Control Award. The European Control Award is to recognize outstanding contributions by young researchers in the area of systems and control. The award is sponsored by the European Control Association and is presented during the ECC every year. The recipient must have spent a major part of his or her career in Europe, and at the time of the nomination must be working in a research institution or company in Europe. This year's recipient is Andonis Papachristodoulou, who is with the Department of Engineering Science at the University of Oxford. And it's my great pleasure to introduce Andonis, who holds an MA/MEng degree in Electrical and Information Sciences from the University of Cambridge, in the UK. In 2005, he completed his PhD in Control and Dynamical Systems at the California Institute of Technology with a PhD minor in aeronautics. And soon after, he joined the Department of Engineering Science at the University of Oxford, where he's now an associate professor in engineering science, a tutorial fellow at Worcester College in Oxford, and the director for doctoral training in synthetic biology. He's an associate editor for the IEEE Transactions on Automatic Control and Automatical, and his research interests are in the analysis and design of networked systems, both technological and biological. So it's a great pleasure to introduce Andonis Papachristodoulou. Maybe I'm thinking that maybe I was selected to chair the session because I'm one of the few people that can actually pronounce his name well.
It's precisely right.
So, Andoni, the floor is yours.
Yeah. Thanks a lot, Mario, for the introduction. And thanks a lot, everybody, for coming. It's a great honor to have received the award, and it's a great pleasure to be able to give the plenary session this morning. What I want to talk about is sum of squares methods for nonlinear systems analysis. This is work that we've been doing over the past, I would say, 10 or so years. And what I first would like to do is pictorially just explain to you where sum of squares sits in nonlinear systems analysis. So we're very much familiar with modeling dynamical systems and understanding simple nonlinear systems using Lyapunov theory, absolute stability. We teach this stuff in our undergraduate courses. But when it comes to more complicated models of nonlinear dynamical systems, such as, for example, this glycolytic metabolic flow here, described by differential equations, things become harder to analyze. And algorithmic tools for constructing the tools that we usually use for nonlinear systems, Lyapunov functions, become too hard. Moreover, when the systems become infinite dimensional, so for example, I give here a fluid flow model, things become harder even still. So what I want to give this morning, and this will essentially be the first part of my talk, is an overview of how sum of squares techniques have been applied to the analysis of many of these systems. And I'll try to give examples from different classes of systems and different analysis questions. But what I will do is I will give you an overview, as I said. The detail and technical detail will be hidden in the papers that I'll reference to. And of course, if you have any questions, we'll take questions in the end. Now, the second part of my talk will try to concentrate on one of the biggest challenges that sum of squares methods face, and that's scalability. So trying to get anything bigger than for 10-state dimensional nonlinear systems is currently a big challenge. But we, as a control committee, have had a significant impact in the analysis of systems that are formed of interconnection of homogeneous agents, like, for example, schooling of fish, or formation flight in aircraft, or even internet congestion control. And in these systems, if you want, the interconnection becomes a parameter in a scalable Lyapunov function. So that was allows to understand properties of these systems independent of the scale. However, as models of complex systems become more accurate, we tend to receive models or develop models of, for example, these signaling pathways in eukaryotes, whose aberrant regulation can result in illness. And we want to understand the robust performance or robust stability properties of the robust functionality, if you want, of this type of systems. And that's a very big challenge. Same with power networks, where now consumers are not just consumers, they're also producers, they're prosumers. Understanding the dynamics of the interconnection of this heterogeneous network becomes a challenge. So there is a question of how, of whether you can take techniques like sum of squares that have been developed for this class of systems and trying to scale them, or whether you can move in this direction by allowing heterogeneity, or whether there is something else that can be done. And I'll try to give you, in the end, an approach for scaling sum of squares that we've been recently developing. But first of all, I said I wouldn't go into too much technical detail, but I'll give you the notation I'll be using. So its notation will be standard. So I would use X for the state, and F for the vector field. It would be a nonlinear vector field most of the time, so this is an ODE in the case of ODEs. But I will allow parameters, parametric uncertainty, for example, or inputs, and then Lyapunov theory becomes storage function theory, and dissipativity theory, and so on. But I will assume that the model has been proposed a priori, so we're not going to go into the model development. And we're interested in understanding analysis questions, not design. It's just an analysis question we're looking at. And the type of analysis questions we want to address is, well, the simplest one is the equilibrium stable, asymptotically stable, and what's its region of attraction? Is there some performance metric guaranteed, for example, if you have inputs and outputs? Is there a safety property that's guaranteed? And that's very useful for cyber-physical systems, for example. Does the dynamical system evolve into an unsafe operating mode, and you want to avoid that? And that you can do for you can answer some of these questions for different classes of systems, such as switched hybrid systems and so on, or even infinite dimensional ones. And I should of course point out that many of these questions are undecidable or hard, so they're getting any answer for these systems would be very welcome. And the tools that we'll be using will essentially be Lyapunov based. So on the dynamical systems end, it will be Lyapunov functions. And of course, I assume that everybody has a good idea of what a Lyapunov function is, but for those who, just a quick reminder, we're looking for a function v, which is positive definite, like a cup if you want, this function here, whose value along the system trajectories doesn't increase. And actually, if it does decrease, then the equilibrium is asymptotically stable. So this Lyapunov function shown here, here's the trajectory of the system. And as the system evolves, the value of the Lyapunov function doesn't decrease. If you now take projections on the state space, you see that level sets of V provide trapping regions for these trajectories. And actually, this is one of the key properties of Lyapunov functions that we like, because if you wanted to do a stability analysis of this system far away from the equilibrium, you'd have to, an alternative approach would be just start doing simulations, but that could be quite expensive computationally. But if someone gives you a Lyapunov function, then immediately you know a region of state space where for which any initial condition will converge to the origin. The problem with Lyapunov functions is that even if someone gives you a polynomial Lyapunov function, then checking one of these conditions, the non-negativity condition, is known to be NP hard. So even if someone gives you a polynomial Lyapunov function of degree greater than or equal to 4, checking those conditions could not be easy. And several methods have been developed in the past to construct Lyapunov functions, because this is a tool that we like a lot. Such as, for example, one of the most useful ones is by Hafstein and Geisel, uses discretization to construct this. But let's look at what happens in the linear case. So in the linear case, the Lyapunov conditions ask for a positive definite matrix P, and this condition, A transpose P plus PA to be negative. And these are the Lyapunov equations for guaranteeing stability of the linear system X dot is AX. And it's a linear matrix inequality. It's a semi-definite program. It's a nice computational tool. We like semi-definite program. We like semi-definite programming because, it's essentially solvable in polynomial time using interior point methods, and you gain all the properties of convex optimization, duality theory, and so on. So essentially, what it boils down to is finding some coefficients yi, which are essentially these coefficients inside P, such as these inequalities hold, these matrix inequalities hold. So in linear systems, we know how to construct Lyapunov functions using semi-definite programming. And the Lyapunov function behind this is just X transpose PX. Now, I said that checking polynomial non-negativity is a hard problem. There is a relaxation of that, which is actually very easy to compute. And that goes back to the 80s. It's sum of squares property. So if I give you a polynomial, and I also that decomposes into a sum of other polynomials squared, has a sum of squares decomposition, then immediately you know that P of X is non-negative. The converse is not true, right? So there are polynomials that are non-negative, which are not sum of squares. But we won't go into that now. Instead, I will show you that the left-hand side is worst-case polynomial time complex. It's very easy to compute, the sum of squares decomposition, whereas, as I already said, the right-hand side is NP hard when the degree of P is bigger than or equal to 4. And the reason it's very easy to compute is because it is a semi-definite program, and that has been known for quite some time now. And what's even more important is that if P of X has unknown coefficients, so if you're looking for a P of X to have a sum of squares property, that's also a convex optimization. So what's underneath this is a very nice property. So essentially, any polynomial P of X that you want to be non-negative, you want to show its sum of squares, it has to have an even degree. So you can always write it as a form in this way, where Z of X is a stack of all monomials up to degree, half the degree of P. So you can always write it this way. Now, if you now find a Q that's positive semi-definite, then immediately P of X is sum of squares. So P of X is sum of squares if and only if there is a Q over here, which is positive semi-definite for a choice of Z of X. The problem, and let me give you an example actually before we do that. So, so here's a P of X. It's a polynomial. It's got an unknown coefficient here, alpha. It's a quartic polynomial. It's order 4. All monomials in it, so x1 squared, x2 squared, are order 4. So I can create a vector Z of X of degree 2 in this case. So x1 squared, x2 squared, and x1, x2. And then I'm looking for a Q inside here. Now, this is a fixed matrix, so these 2 here corresponds to this entry there, for example. But then I have this alpha times x1 to the 4. That's this corner here. But then I get these other matrices, like this one here, which essentially say that, this vector times this matrix times this vector is 0, because the entries in this vector are not independent. The last one squared is the first one times the second one. And this one says that 2x1, x2, 2x1, x squared, x2 squared is equal to those 2 entries. They're balanced out. So what I'm essentially saying is that there is no unique Q that will do that. It's actually an affine variety, an affine family of them. So it's a constant Q plus a sum of other variables times qi. And if you find one of them that does the job, you have that p of x is sum of squares. So this is, of course, an LMI, a semi-definite program. And so we go back to the tools that we're traditionally used to in linear systems analysis. This becomes a semi-definite program. The challenge that I'll come to in the end is that these QIs are quite large. I mean, you can imagine that if you have many variables, let's say n, and the degree of p is 2D, then these QIs can be quite hard, can be quite large. Okay, so we have developed software, and other people have done that as well, because nobody wants to actually, start, finding all these matrices and constructing them. So this software that we developed takes a sum of squares program, turns it into an SDP, calls a semi-definite programming solver, and gets the solution. So it's a parser, essentially. And there are other programming solvers, and you may have used YALMAPE, which also has a plugin for sum of squares. So let's go back to our Lyapunov theory. Well, what we're looking for, essentially, is a Lyapunov function of this form, z of x transpose p z of x. And for now, I'll assume that f is polynomial as well, because if f is also polynomial, this also becomes a polynomial condition, affine in the unknowns of p. So then I can immediately set it up as a semi-definite program. And what I'm doing is essentially taking the non-negativity conditions, doing something similar to what we do in LMIs when we have definite conditions. We subtract an epsilon times identity term in order to make it semi-definite. So here I'm going to subtract from it a positive definite function phi of x constructed in a very in a nice way, if you want. And then I get these non-negativity conditions here. And I'm now ready to do the sum of squares relaxation, and now I have a semi-definite program. So it's a routine approach to construct semi-definite programs using sum of squares. And I can give you a nice example. You can try it by hand if you want. So this is a 4-state system with a cubic nonlinearity. If you try the find Lyap command in SOS tools, no quadratic Lyapunov function exists. A fourth order one pops up, and this is the one. So essentially, you're done. And you can do other questions as well. You can do this type of stuff. So you can now start calculating the region of attraction of the van der Pol oscillator in reverse time. So this is the quadratic Lyapunov function that you get. And then this is the fourth order, the sixth order, the eighth order. And you can see how now you can get closer to the boundary of the region of attraction. Now, you might say, hang on, this is now local stability analysis. You're constructing your Lyapunov function locally. Indeed, yeah, so this is the second thing I wanted to put to, the second message I want to send today. If we want the derivative condition only to hold on a region of the state space, so for example, this ball of radius square of gamma, all I need to do is a procedure similar to the S procedure. And what I'm asking, for example, in this case is I'm adjoining this constraint, a of x is less than or equal to 0, to the derivative condition using a sum of squares multiplier p of x. So now you can have constraint status function locally, so within a region. This example here was constructed essentially by iterating between the shape of D and the Lyapunov function you get. So I should also mention that these now links is a result that comes from real algebraic geometry. It's a representation theorem, as it's called. Because essentially what these methods do is combine semi-definite programming, Lyapunov theory, and real algebraic geometry. And this representation here is nothing but what's called the Putrinar's positive Stellensatz for checking non-negativity of polynomials over compact sets. So there's a bunch of examples, a bunch of applications that you can now do, and I already showed you estimating region of attraction of equilibria. But there's also a number of people in this audience and beyond that actually contributed decisively in sum of squares method, and I'm sure I've missed people out. in this list, and it was not, it wasn't intentional, I have to say that. But there have been quite a lot of questions that have been addressed on different systems. So for example, robust stability analysis, we have uncertainty, performance analysis, input to state, state to output, input to output, hybrid switch systems, stochastic systems, time delay systems, PDE systems, also different analysis questions such as model invalidation, hybrid verification, and controller synthesis, but I'm not going to talk about that today. What I will do is I will take you through a number of examples. So I'd like to do that rather than give you different frameworks, that they've been applied to. So I'll give you examples from systems and synthetic biology. It's an area that I work a lot now. Aeronautics, aerospace, fluid mechanics, network systems, and process control, to essentially illustrate some of these applications. So the first example I'll give you is from systems biology. So this is a model of heat shock response in E. coli. So this is when you've got cells that suddenly change the temperature, the cells have to react in some way in order to avoid the proteins forming aggregates and them dying. So there is a whole feedback mechanism inside the cells that tries to react to this temperature change. So we developed a model with Hannah El-Samad that is essentially a DAE model with a rational vector field. And we asked the question, is the response robust to changes in two of the parameters here, these eta and alpha s? Now, the equilibrium of the system will change as these parameters change. This is what happens usually in nonlinear systems. And we consider parametric uncertainty. So if you look at now this region here of parameter space, if I pick a point here in parameter space, then I get in my parameterized Lyapunov function, which is what sum of squares produces, I can plug in that parameter in there, and I get in state space the level curves of the Lyapunov function. As you can see now, the equilibrium has also moved from its nominal value, 1, 1, there. And if I pick another point, you go in another direction. So this is essentially how one parameterized Lyapunov function can do robust stability analysis of, well, this is a simple two-dimensional system, but it's got two parameters as well. When it comes to performance analysis, you can do, you can do input to state, state to output, and this is an example we used on the FA18 model. It was a simplified model of the dynamics in 2 dimensions. And then you get these plots that say, for example, that if the aerodynamic derivatives have uncertainty weights, and you pick, for example, 0.4 to be the weight, then you're looking at the diamonds, and for an input energy gain of 0.1, then you get a reachability, for example, that the delta alpha can't deviate more than 6 degrees. This is that kind of information that you can get. Now, one of the things I said before, and this is one of the questions that you might ask, is you can do polynomial systems or rational systems. Can you do non-polynomial systems? And this is an example of a chemical process in which the reaction rate constant is not constant anymore. It actually changes with temperature itself. So you get this Arrhenius type change in the reaction rate constant, but also temperature appears as a state. So it's a non-polynomial vector field. And we found a way to address this type of systems through a recasting approach or through an embedding approach in this paper. And here you get, again, Lyapunov functions constructed algorithmically. Moving on to switched and hybrid systems. So these are systems that have dynamics that, well, when they hit a switching surface, they change direction or they evolve in another mode. So you've got 2 modes. In this case, the invariants of the 2 modes are overlapping. So you switch between one and the other when you hit essentially this switching surface. And when this switching surface opens up, so when it moves, you see the gradient changes, the equilibrium becomes unstable. So computationally, you can find that P at about this P, you can, it becomes unstable. So using a framework developed in the late 90s by Branicki using multiple Lyapunov functions, we were able to construct a Lyapunov function for this system going very close, order 8, for example, you get for a P very close to the limit of stability. Now, on the industrial end, we've had quite a few requests to analyze industrial applications. So this was an example from Honeywell back in 2007, where they gave us a model of a life support system for astronauts, essentially on a mission. So the model that they gave us was quite challenging. It had 6 modes. It was in a hybrid system, a switch system, hybrid system with 6 modes. Each mode had 10 states, and it was nonlinear. It had, I think it was cubic nonlinearity in each one of the modes. And they wanted to show that the oxygen levels would not go too low, for example, if this system operates well with their designed controller. So we used a framework that is called using barrier functions to construct a barrier certificate for this system that guaranteed essentially the safety of this model for this example. And we later on in 2010 we were part of a project with the European Space Agency, where they are interested in the Mars sample return mission, which is, well, I don't know if you know, it's a mission that was trying to bring back a sample of Mars to Earth. So the last part of the mission involves a catcher that will catch the capsule that will go into orbit around Mars, and they gave us a model of the final approach to catch the sample, which we analyzed for safety using barrier certificates. Again, the uncertainty here was on the thruster misalignment. So I gave you a number of examples from down here, I would say, of different questions we can answer, different types of systems we can consider. There is one class of systems that I would like to spend some more time on, and this is infinite dimensional systems. The reason is that there's a third message, if you want, that I wanted to send of questions that you can answer using sum of squares. So let's first start with the simplest type of infinite dimensional systems. That's time delay systems. So in this case, you have a system of the form x dot is involves time delay tau, and now the state in the system is a function, because in order to propagate forward, in order to solve, if you want, this differential equation, you need information from tau seconds all along for the first tau seconds. So the whole trajectory tau seconds ago is the state. And of course, a Lyapunov function is a function of state. And if the state is a function itself, then it becomes a functional. And here is a functional that is that has a structure that's rich enough. It's necessary and sufficient. It's a complete, as it's called, Lyapunov-Krasovsky functional. So if you manage, this is a structure that's necessary and sufficient for stability. And constructing this has been quite a challenge for quite a long time. I mean, in the late, I think the late 90s, Keagin Gu provided an approach for discretizing these conditions and provide LMIs to solve it. What we did with sum of squares is we asked for the positivity of each one of them separately. We tested those using polynomials. So we developed with Matthew Peat an approach for testing this condition using essentially what are parameterized LMIs. In this case, if M of S and T of S are polynomial, this is what polynomial matrices, this is what this looks like. And same for this condition. But the reason I'm showing you this is that I think solving parameterized LMIs of this form is something that sum of squares can also do. And essentially, you can treat these as sum of squares matrices. And Hall and Scherer did a lot of work on this back in the in about a decade ago. One of the ways you can see this is that you can introduce new variables, y, to turn this condition, which is a matrix having these S in them, which vary in a domain. You can turn these into non-negativity into a polynomial, which you can then adjoin this condition here that S needs to be between tau and 0, minus tau and 0, using a multiplier, just as the way we did local stability analysis. This immediately means that you can do stability, and you can do stability now of nonlinear time delay systems as well. So we did this predator-prey model with time delay in the way the predator benefits from an interaction between the prey and the predator. And you can construct this type of Lyapunov functionals using sum of squares quite easily, and you get very close stability conditions very close to the boundary. So the reason I wanted to talk about infinite dimensional systems is because of a recent project that we've been involved in to try to understand stability of, or to understand properties, if you want, of classes of PDEs. And this is a very different problem. And just for a second, I'd like to show you how you can get a conclusion about, for example, exponential stability of these very simple PDE using energy functions. So what you do is you would consider a function, or an energy function, which is just the energy, half times the integral of u squared d, the space d eta in this case. Now, when you take the time derivative of these, you end up with u times ut. You can plug in for the dynamics here. So u eta eta stands for the second derivative of u with respect to eta. So you get this. And now, in order to get any conclusion, in order to make these negative definite, if you want, that's your objective, you need to follow an approach that involves integration by parts. That's the first step. That gets the boundary out, the boundary values outside, which then you can use the boundary conditions to eliminate these. But then you're still left with a first spatial derivative of u and a positive term here. So you need to now relate u eta to u in some way. And there are a bunch of inequalities out there. There's a Poincare inequality in this case that actually relates these two. And now you can get something that's only a function of u squared. You can get a condition on c versus lambda and relate that to u to get exponential stability. So that's how it's usually done by hand. And you get your condition. So what we did in this project is we now extended slightly the, well, it was challenged in its own. So the structure of these functions v to be now much richer. And the question was whether making a quadratic form with a p of eta, for example, spatially varying coefficients in there could actually give you interesting results. And the reason I insist on this is that it has found interesting applications in fluid mechanics that I'd like to talk about in a bit. But before I do that, for example, you can now see how you can extend the classes of systems you can do analysis. So this is the same example, but now with the spatially varying coefficient in front of you, and you can construct this type of Lyapunov function quite easily using sum of squares. And get these function for p of eta, for example, a function of x. But as I said before, there is an application that I'm actually I think it's very interesting. I mean, I have a special interest in fluid mechanics, but I think it's very interesting in itself because it's a question that has been around for quite a long time. It has to do with stability of shear flows. So there's a flow between two plates. You take the top plate and you move it, and you get this flow that looks like a triangular flow moving along. So if you do the linear stability analysis of this flow, you get that this is stable for all Reynolds numbers. If you do experiments, you get turbulence in 300 for Reynolds numbers 300. And this has been a question of why is this so? Why is stability theory not correspond to transition, and why stability theory is so far out. So there's been a lot of research in the past 10, 15 years on linearized models versus nonlinear models, open models, models with inputs and outputs versus not. There's a similar flow, which is between two concentric cylinders, so shown here. If the gap here is much smaller than the radius, the two flows are not very, very different, actually. So what I'm going to do is I'm going to assume that everything is streamwise constant, which means that if I take a cross-section here and a cross-section further down, I get the same flow. So this makes the flow essentially 2D rather than 3D. And I will try to construct Lyapunov functions and this type of functions, energy functions, using sum of squares. So the model becomes this horrible mess. There's two things I wanted to point out. So there's this pressure term that's always challenging when you do analysis of fluid flows. There is this F term here that only appears if you're looking at this type of flow versus this type of flow. For this flow, this term is 0, this F. And I'm also allowing for an external disturbance because I also want to do input to state, input to output properties, try to get gains. And how they change with the Reynolds number. Okay? So the worst stability, and this is known, that you get for this type of condition, for this type of flows, is when this rho parameter is 0.5. Because then the two cylinders move, one moves clockwise and the other one anti-clockwise with the same velocities. So the Lyapunov functions I'm going to construct are actually not very complicated. And this is the thing. They're just the energy, but weighted. It's a weighted energy function. And this function allows me essentially to get rid of the pressure term and some of the nonlinear terms. So it's very useful to actually use this function. But it's enough to show that, for example, when rho is 0, you get infinite stability for Reynolds, which is what we knew already for Couette, because Couette is down here. And that the worst stability limit is right in the middle of this graph for rho is a half. Okay, so that's with this very simple Lyapunov functional. Moreover, if you now zoom around changing the Reynolds number and looking at around rho is 0 and do an input to state calculation, looking at induced L2 norms, you see that as Reynolds number increases, as you increase Reynolds number around this point, then the gains go up as you would expect because you're coming very close to becoming unstable in this regime. And what's the most interesting result is that the way the gains change with the Reynolds number corresponds nicely with the linear stability analysis that was done by Bami and Dale and Bami and Jovanovic earlier in early 2000, which is that the Reynolds number scales like linear for low Reynolds number, the gains scale linear and then quadratic for higher Reynolds number. So this is a nonlinear stability analysis, if you want, using sum of squares, using a very simplified Lyapunov function, but which actually recovers some of the results that you've seen in linearization. So what I wanted to do now, I think, is to go back and to take a step back and consider the problem up here. So the problem of scaling sum of squares. I've shown you examples of systems down here, and we went through a path of quite easier, more challenging questions, and so on. But the thing is that it would be nice if you could actually start understanding the robustness, for example, of much bigger nonlinear systems computationally. But there is a challenge in using sum of squares. I hinted on this in the beginning of my talk, and I'll go back now and try to concentrate. So essentially, can we ever understand systems of this form? So this is the epidermal growth factor pathway in mammalian cells. And this, if this doesn't work the way it should work, then growth factors could result into cancer, for example. So aberrant regulation of these pathways can result in disease. So what's the problem? Well, the problem is computation, as you can imagine. So I mentioned before that, well, checking whether P is a sum of squares can be written as a sum of other functions squared involves writing it into this quadratic form and looking for a Q that's an affine family of other Qs. So that's an LMI. Okay, so that's what we said before. And then I said that, well, it's an LMI, but then these QIs, these matrices here, their size grows really fast. Okay? It grows polynomially if you fix both the number of variables in X and the degree, the 2D is the degree of P, so D if you want fixed. So if you increase the number of variables or you increase the degree, but if you increase both, it grows exponentially. It grows really fast. Okay, so can you do something to tame the growth, if you want, of these matrices? And several people have looked at these. So there's a result by Resnick and on sparsity of polynomials using Newton polytopes, which essentially tells you that, well, if P of X is missing a lot of the monomials, you actually don't need Z of X to be all the monomials up to degree D. So you can get away by only putting a few of them in your Z. The other thing you can do is reduce the number of decision variables. So now you can crank down on the number of lambdas or the number of decision variables in your problem. So that's another thing you can do. Take into account symmetries, group properties, and that actually works pretty well. If there's a symmetry in P, then you can now start doing structures in your SDPs and in your polynomials in their representation, if you want, and which translate into structures in SDPs. You can structure the decomposition, okay, and quite a few people have looked at that. We've also did some work on decomposing, but now on the SDP end, and that's what I want to talk about in the very end. Or you can relax the problem altogether, okay? And this is some recent result by Ahmadi and Parillo, which rather than asking for P for these to be LMIs, they relax them into linear programs by essentially asking for these conditions to be diagonally dominant. So the first thing I want to say is quickly that one of the approaches we developed, a few years ago, that essentially breaks the system into subsystems in a clever way, not in a naive way. So it breaks the systems into subsystems so that you can get a diagonal Lyapunov function out of it. So that then makes the system really sparse, not a lot of decision variables. So this now is much easier to construct. And we've been able, for example, to look at systems with 16 states. If you do it directly, you wouldn't be able to parse it. But we've been able to break it up into 3 subsystems and design and construct a composite Lyapunov function for this. But the one approach that I think is more promising of all, and which I want to spend the rest of my talk talking about, has to do with decomposing the semi-definite program you get at the end. And this is a result that, well, it's been around for a long time, but it's receiving a lot of attention recently within our community as well. I know Anders Ranzer has been working on this. Actually, this is where I first heard about this type of systems was from him. So, so this is work with Richard Mason, and this work received the Hugo Shuga Award this year. So the idea is use chordal sparsity to decompose semi-definite programs, and you can do that. First of all, let me just explain what a chordal graph is, and I'll go a bit slowly here because I think this is important. So if you have a graph that has a cycle, a simple cycle of length bigger than or equal to 4, that's not a chordal graph. So a chordal graph has to be a graph which, if every simple cycle of length bigger than or equal to 4 has a chord. So what you can do in this case is put a chord there and make it chordal. So you can add chords, you can chordal extend these graphs to make them chordal. And we can recognize chordal graphs very easily. That's good. So for example, a complete graph is chordal, and so is a tree. But the other thing next thing I want to introduce is the idea of a clique. So here, for example, these 4 nodes form a clique because if you take them isolated in the graph, they're fully connected. But there's a clique within that clique, and that's these 3 nodes, but that's not a maximal clique. I'll call maximal cliques that are not cliques, sub-cliques of other cliques. So maximal clique is a clique that's not a subset of another clique. And cliques are important for chordal graphs and for decomposing SDPs because the maximal clique in a graph will determine the size of the SDP we'll get in the end. But hold on a bit, I'll show you how this is done. So the next thing that I need is the relationship between the sparsity of a matrix and a graph. And I think we're more familiar with this given all the work that we do in multi-agent systems. So the sparsity pattern of these matrix is represented by the graph because, for example, the 1-3 entry has a missing edge on the graph. So missing edges on the graph correspond to zeros on the matrix. And I'm interested now in whether this matrix is positive semi-definite. Okay? Is this matrix positive semi-definite? And there was a result back in the late 80s by Agler and McCulloch and Helton that said, yes, it's positive semi-definite. The only thing you need to do is check that the submatrices corresponding to the cliques of the graph, okay? So if the sparsity pattern of Z is chordal, then all you need to do is check that the submatrices corresponding to the cliques of the graph are positive semi-definite and they sum up to the original matrix. So it's decomposing the positive semi-definite matrix. So let me do it pictorially because I think it's easier if you do it this way. So now here's a graph. I've numbered the cliques, the maximal cliques in the graph, and I've color-coded them as well. So this is a submatrix this corresponds to. So I break the graph into its maximal cliques, and that breaks the matrix into submatrices, which are quite tiny, as you can see, which sum up to Z. And instead of now asking for Z to be positive semi-definite, I'm asking, do there exist submatrices corresponding to the maximal cliques A, B, C, and D that sum up to Z? And now this decomposes this matrix. It actually decomposes the SDP as well. And there is, Lieven Vandenberger has a software that actually does this for you. It looks for chordal sparsity patterns, decomposes SDPs, and computes. So obviously, this is one side of the picture. The full picture involves its dual, and the dual, if you're familiar with matrix completions, is over here. But I'm not going to go into that. Instead, I'll show you the result that we looked at. So what we looked at is the question of very simple Lyapunov function construction. So linear system, sparse. So a large network with quite a lot of sparsity in it. If you now blindly go and ask for your semi-definite programming solver to construct a P that is full, immediately you're going to get a full P and a full derivative condition to check. And that's now a very dense SDP, and you're not going to be happy. It will take quite a long time. It's not only that it takes time, it's also ill-conditioned. It will become ill-conditioned, and then you'll not get a reliable answer. So instead, what we looked at is construct P chordal. And remember, complete graphs are chordal, so we can actually add edges, consider denser and denser Ps. But try to control the derivative condition so that it's also near chordal, or so as to exploit chordal sparsity. And indeed, if you do that, now you can see how the chordal decomposition reduces significantly the burden in constructing Lyapunov function for these 3 classes of systems, for which we've shown that both P and Q can be chordal by choice of P. Of course, you can, as I said, you can go denser and denser in P and go to the complete graph, which is the case, which is also chordal. And so we have an iterative algorithm for checking. So the message is, rather than going directly into full, start with something then sparser. If you get the answer, you're home and dry. Otherwise, you can go and look for more complicated stuff. And we also did it for for graphs that are not chordal, are just random graphs, and indeed you get here the same computation. So the last question we looked at was whether this approach could be used for sum of squares. And there has been also some work on that for polynomials. Can you construct, can you take this type of sparsity into account for testing polynomials by Wacky and Lasserre? But what I wanted to give you now is what I think is the current, the best result we currently have. It's a system with 100 states, cubic nonlinearity, local stability analysis, but it's quite sparse. And if you now take, this is the correlative sparsity pattern of F, so it's 100 by 100, so if a dot appears here, that means xi talks to xj. And now you can turn the Lyapunov conditions, the sum of squares Lyapunov conditions, and start increasing the monomials, if you want, in V, add monomials in V slowly, making sure that both the first condition and the second condition has the SDP underneath has a chordal sparsity pattern so that you can decompose it. And indeed, so we were very careful in how we were searching for these monomials. We constructed a V that had this correlated sparsity pattern. The derivative wasn't a complete mess. You can see now it's a bit denser, but not too dense. Dense enough that you can decompose it into its chordal sparsity pattern. So the SDP constraint was decomposed, and in just above a minute, you could actually construct a Lyapunov function for this system. Okay, so I'm coming very close to the end of my talk. So what I did is I started off, I gave you examples from this corner here, if you want, of systems that are simple. You can do different types of analysis questions, region of attraction, and so on, robust stability, robust performance, more complicated, even fluid flow models. And then on trying to answer questions about systems over here, and ended up with chordal decompositions. I should say that there's a number of things I didn't talk about, I didn't have time to talk about. There's a lot of work on doing synthesis using sum of squares. That's a non-convex problem, but there are ways, there are approaches, of course, to address, to be able to construct controllers, in this case, that guarantee, for example, a certain performance index. There are other application areas that I didn't talk about, such as power systems. We're currently looking at 2D PDs, more richer fluid flows, essentially, output functional estimates. There are lots of questions you can now start asking about, interesting questions you can answer about PDs. There are other scaling approaches for sum of squares that I think are obvious, like, for example, can you do model reduction before you use sum of squares, keeping track of some error? This is something we've tried to look at in the past. We do try to develop algorithms and software for every class. So, for example, Giorgio gave a talk on Wednesday on constructing functional inequalities using sum of squares. And then, as I said in the beginning, I spend most of my time working in synthetic biology, and there's always a question I ask: is there a framework now that you can be used for using sum of squares for synthetic biology, but also for synchronization consensus of heterogeneous agents now, using, for example, chordal sparsity. And last but not least, I should say that all the papers are available on our website, and you can, if you have any questions, I'm here for the rest of the day if you want to ask anything. I'm more than happy to help. I should at this point thank everybody, all my supervisors, collaborators, postdocs, students, and friends at Cambridge, Caltech, Oxford, and elsewhere. And I should definitely thank the Engineering Physical Sciences Research Council, who has been supporting us well in the past, as well as the BBSRC, the Biotechnology and Biosciences Research Council, over the years. So these are some faces of people that actually did most of the work. So Richard Mason, who worked on chordal sparsity, Reza and Giorgio has been working on the PD end of things, and James on the decomposition. And well, thanks again for coming and for listening, and I'm happy to take questions. Is it?
We have time for questions. Questions at least. Can you wait for the microphone?
Microphone.
Hi.
Hi.
Thanks for the really great talk. My question is about extended formulations and the application in control. So sum of squares can be seen as a lifting of the problem on which LMI methods work better, right?
Yep.
But now in optimization, people are maybe much more excited by extended formulations. Well, maybe it can be seen actually as a follow-up on sum of squares.
Yep.
So, but I don't know of any applications in control. Do you think it's promising, or?
You're asking whether there are applications for controller design in using sum of squares. Is that the question?
But the question is more applications of extended formulation, where these methods, you know, like people like Reka Thomas and Parillo are working on for the moment, are they already used in control, like extended formulation methods?
I'm not aware of, no.
Do you think it's promising?
Yeah, I think I think it's promising. Yeah, it's. I think applications in control in general of sum of squares for the control design is definitely something that deserves a lot of attention. Yeah.
Thanks.